Welcome everyone to the 2020 APEC Groundbreakers virtual tour by APEC OUC. This year, our event would be the biggest one ever done, with 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it would cover sessions in 4 different languages. Please remember to register for as many sessions as you can. All sessions will be available for replay as many times as you want for 2 weeks after the initial session date and time. You can also interact with the speaker at any time during those 2 weeks by posting questions or comments directly in the playback session page. I would like to say thanks to all Oracle user groups and Java user groups that made this event possible, and also to our sponsors, Oracle Groundbreakers and CloudDB. Now for today's session, Partitioning, Bigger and Better by McDonald. Please feel free to write questions at any time during the session using the Q&A tab of the Zoom webinar, and the speaker would be answering them at the end of the session. If you experience any issues during the presentation, please feel free to contact me at any time using the chat tab of the Zoom webinar. Now, without any more delays, I would like to leave you with this amazing session by McDonald.
Welcome everyone. Melanie, can you turn my webcam on, please? Not to worry, time is of the essence, so we'll simply charge on regardless. Okay, hopefully you can see my screen. You probably can't see me, but that's okay. Let's focus on the screen for the rest of this session. My name's Connor McDonald, and my, oh my, have we got a lot to get through today. So we're going to charge in very, very quickly. Today is Partitioning Bigger and Better. It's actually a follow-up to a session I've done for a number of user groups called Partitioning 101. So we're taking that and moving forward. I live in Perth. It doesn't look like that right about now. It's mid-afternoon and it's just crossed over about 38 degrees or 100 Fahrenheit if you're in that part of the world. So it's a little bit out of control. I love talking technology, so this is how you get in touch with me. You can get me on Twitter, that's probably the best way, or my blog or my YouTube channel. The Twitter handle will be at the bottom of the slides throughout. If you like attending webinars, and hopefully you do because you're on this call, we run a thing called Office Hours, which is literally product managers in Oracle giving webinars every single month. We've run over 400 of them and they're free. And if you prefer to have a dedicated session specific for your customer, a topic that you would like to explore, reach out to us. We can actually do private office hours sessions. We call them office hours at customer, basically for your own department teams. Now, before we begin, I say this at all my talks nowadays. This is obviously a fairly disturbing picture, but I just want to reinforce that we're part of a community here, and obviously to have a good, prospering community, we need people in it that are actually alive. That would help. So please stay safe, stay healthy. One day we'll meet each other in face-to-face again, and it would be a tragedy if we lost anyone before that time. So why bigger and better? Way back in version 8 is when partitioning came along. It's been around for a long, long time, but the premise is fairly obvious. You have something big and you make it smaller, into smaller bite-sized chunks. It generally makes things easier to manage. But if you fast forward to today, generally the kind of techniques people were using way back in Oracle 8 pretty much haven't changed that much. And yet partitioning as a feature has evolved hugely. So I wanted to cover some of the things that have come in the more modern releases that some people aren't aware of. To do so, I'm going to establish a very quick baseline. This is effectively the next bunch of slides is the things I'm actually not going to talk about, just to establish where I'm assuming we're all at. So we're going to establish a baseline on the core parts of partitioning. So we'll start with tables first. We should know about range partitioning. Effectively, we define a list of partitions, always with the values less than, and time is the most common attribute we tend to use. It's a split by an upper bound. So as a result, when I have a partition definition, something like this, Partition 2 is defined by the value it's defined by and the previous partition. So those two values define the scope and size of partition P number 2. We also have hash partitioning. The reality is big stuff is a plane. You know, the telephone book, when it got too large, what they do, they broke it into multiple bits. For anyone on the call that doesn't know what a telephone book is, you're obviously too young, and I'd like you to leave the call immediately. So the way we do hash partitioning is we partition by hash and we nominate a number of partitions. So all it really does is simply use a hash function to spread the values out across multiple segments. So if I had a table with 8 partitions and I said I'm going to put 100,000 rows into that table, then later on we can see that about 12,500 rows went into each of those physical partitions. That's hash partitioning, simply dividing and conquering. We have list partitioning. List partitioning is simply where when you want to handle a number of smaller values, range or hash generally doesn't make sense. So partitioning by list lets us nominate specific values. If I'm breaking a table of tourism up into cities in Australia, I might have a partition for Perth, for Sydney, for Melbourne and Brisbane, etc. For small discrete values is when we use list partitioning. We don't have to have just a single value. We can have multiple values that go into a single partition. And we can also have a catch-all that lets any values that don't appear in our explicit list to actually fall into this one. We also have composite partitioning. I spoke about the telephone book. Sometimes one level is perhaps not enough. I used to visit India, a fantastic country, and it doesn't matter if you split their telephone book into multiple chunks, there's still very, very big telephone books. And so composite partitioning is where we have a high level of partitioning, for example, by range. It can be any of the partitioning types. And then we break each of those partitions up into subpartitions. So in this case, it's range followed by a list. That's a way of effectively multiple levels of partitioning, limited to 2. We also have interval partitioning. The problem with range partitions is we had to make sure we had them predefined. So as a DBA, I often got caught out about this. My last partition in a table would be partition 2019. The year would tick over to 2020, and all of a sudden I could no longer insert data into my sales table. Interval partitioning insulated against this by having what we call an interval size here. We still have our partition defined, but when we define intervals now, partitions are created as required on the fly. So if my current high timestamp is 2018, I can still come in and insert something for December 19, no problems, and I actually dynamically create a partition as I go. We also have reference partitioning. If I have a sales table that is actually massive and I have a sales date to partition it by, then it makes sense that any child table of that is probably even more massive. The problem is that child table might not have a date column on which to partition. I'm going to partition it by a foreign key back to its parent. And we can do that with reference partitioning. My table's called sales, it's partitioned by date, and it has a primary key as you'd expect. My sales items, a child table, can simply by nominating a foreign key back to the parent, partition on the same scheme as the parent. As I said, this is our quick baseline. I have partitioned indexes, and we'd be familiar with the two kinds of indexes we have on partition tables. We have a global index, which is my table is partitioned, and I create a standard index, so it's one segment that spans all partitions. I can also have a local index. That is where I simply use the keyword local, and now the index itself is also what we call equipartitioned. That is, the same partitioning scheme is adopted that of the base table. We have partition queries, and most of us are familiar with the benefits of partition queries, which is if I have a table which is partitioned, in this case it's partitioned by monthly, and I put in, say, 1 million rows spanning those 12 months, then when I do queries with the partition key, I don't have to span all the entire table. I get to do what we call partition pruning. In this case, I can see I did partition range single, so I only had to scan a single one of those partitions because the timestamp was the partitioned key. And finally, on our quick baseline, we have partition maintenance. Namely, we have all these facilities to do maintenance operations on partitions. We can split them, we can drop them, we can truncate them, we can merge them, we can exchange them. How fast was that? As I said, this is establishing a baseline for the things I think that we all share and know already about partitioning. If you're new to partitioning and you're going, oh my goodness, that was trailblazingly fast, I recommend this. Go to asktom.oracle.com/partitioning for developers. It's a much more gentle walkthrough the core components of partitioning we've just covered there in literally just a few minutes. And as I said, if you're brand new to partitioning, contact me. We can do a dedicated Partitioning 101 session for you. But as I said, this is about bigger and better. So that's the baseline. That's the thing I'm assuming that we're all comfortable with. So now we're going to go into each of those topics again: tables, indexes, queries, and maintenance, but dig deeper and look at some of the more recent features. The first one is, let's explore hash partitioning a little bit more deeply. The key thing here is, I just want to say, is it's important that you have a power of 2 whenever you're doing hash partitioning, which means when you create a hash partition table, the partitions you nominate should be 4, 8, 16, 32, etc. Now the question is why? Why would we do that? Normally a hash function scatters rows evenly no matter how big the hash distribution is. Let's look at a simple table of 8 hash partitions. It's following the rule, and I'll put 100,000 rows in there. As we saw in our quick baseline, that gives us about 12,500 rows for each partition. Let's now go against the rule. I'll do 5 partitions and insert the same 100,000 rows. You would expect for 5 partitions, I would get 20,000 rows for each partition. 100,000 divided by 5 is 20,000. But we don't. What we actually get is this. 2 of the partitions will have 12,500 rows. 3 of them will have 25,000 rows. That almost seems like a bug in the hash function. We can actually prove that by using a probe into DBMS row ID. We can see the real numbers there. 2 of 12,500 and 3 of 25,000. That's actually done deliberately. We didn't do this because there's a bug in our hash algorithm. The problem is, why do we have hash partitions in the first place? In order to be able to carve up things into smaller chunks. If 5 is not enough, I might want to make it 6. What happens is, the reason we do it this way is when we come to split a partition or add another hash partition, we don't have to redistribute all the data. We only have to move 1 and split it into 2. If I broke up another hash partition, I would pick the highest one and split that into 2. We do it deliberately such that we only ever have to split 1 hash partition rather than recarve up the entire table. Let's dig a bit deeper into composite partitioning. As you probably saw from that quick baseline, you get a lot of very long DDL once you start nominating a whole stack of partitions and then a whole stack of subpartitions inside it. To fix this, we have a concept called subpartition templates. This is something that's rarely used, but it's actually a very, very nice typographic convenience. If I'm partitioning by range and subpartitioning by list, I can define a subpartition template which will be applied to every single partition. So each of these partitions will actually have 4 subpartitions without me having to focus on it every single point in time or type it in every time. That's cool as long as you know that every partition is going to have the same subpartitions. The reality is, one of the motivations for composite partitioning is that you might not want to have the same number of subpartitions in each partition. For example, my database may have a lot of data for 2017, a lot for 18, a lot for 19, but come 2020, sales may have absolutely dropped through the floor because of COVID. The motivation for partitioning is sometimes to have equally sized chunks so they can be easily moved around, get better, same parallel query performance, etc. What if one of my partitions is tiny? Can I address that with composite partitioning? Well, I can, because not every partition needs to have the same subpartitions. For example, 2017, a big year, has 4 subpartitions. 2018, a big year, 4 subpartitions. But 2019 might just have 2 subpartitions. I can do that. 2020 might have no subpartitions. And as a result, be aware that with composite partitioning, a partition at the high level may be physical, like this one, it actually is a segment in its own right, or it might be logical. This one here is logical. It actually consists of 2 physical subpartitions. So you have that flexibility, but also have that awareness that every partition in a composite partition table might be just a logical one, or it might actually be a physical one. Let's dig into interval partitioning a little bit more. As we saw when we create a dynamically created partition that comes as part of an interval, is we lose control of the partition name. It has a sys-generated number. You can actually control it yourself, but until that point in time, how do I actually, for example, do an operation on it? How do I move it? Do I have to go look at the data dictionary every single point in time? I don't. The first thing I can do is I can choose to rename it. And that's a common technique we do. We see a dynamically created partition and then we rename it to something that represents its real value. But if you don't want to do that, we have a thing called the for syntax. And all you have to do is say, I want to do something with a partition for the partition that contains this value. And the database will look at that value, go find out what partition you're referring to, and then you can do a move or a drop or a truncate, etc. So if you're using interval partitions, you don't actually have to know the name of the partition. You can actually just use the for syntax to do partition maintenance operations. What about existing range tables? If you've got an old database that's using range-based partitioning, and therefore you're constantly having to do maintenance to actually add new partitions, you might want to convert to an interval partitioning scheme. And you can do that very, very simply. All you have to do is actually set an interval, and the job is done. Here's my existing range table, which had explicitly defined ranges, and then I simply say, from now on, I want to use intervals of a month. The existing partitions will stay as they were, and all new partitions will become 1 month intervals. You need to be a little bit careful with 12.1 because in 12.1, if you've done this conversion, at least one partition must be one of those original range-based partitions. Therefore, you might have some troubles when it comes to dropping it. Once you get to 12.2 onwards, all that is solved. Let's now dig further into some of the partitioning features that are available in and above those that we've covered in our quick baseline. We can now have partitioning on virtual columns. Now, what would be the benefit of doing that? The main benefit is when it comes to what I call terrible design. I might have a list of orders here from my orders table. It's getting very, very large. I'd like to partition it on financial year. I go look and I go, where's the financial year? And due to this fantastic design, sarcasm intended, turns out that the financial year is tucked away in the invoice number. That's obviously going to be a bit of a nightmare to actually partition on. What I can do is take my table and either add or create it with a virtual column. In this case, I'm using financial year. It's a generated virtual column, and it's actually to number of the 3rd to 6th character of the invoice number. 3, 4, 5, and 6 gives me the financial year. I can then partition on a virtual column. So even if I don't have an exact column that I'd like to partition on, if that information is somewhere in the table, then I can actually partition on that. If that would actually break my application, for example, they don't want to see another column, I could even make that column invisible. So I get some of the benefits of partitioning without actually the application even being aware of it. One thing that is not there yet, which would be nice, but it is coming, I'm hoping, in a future release, is what I call transitivity. So ideally what we're hoping is one day you'll do a select where invoice number equals something, and we'll know that that invoice number is in some way related to a partitioning column. We'll dig into your query predicate, find out the financial year, and therefore be able to limit the actual size and scope of the query. That's not there yet. The only way you'll get things like partition pruning is if you actually explicitly reference that virtual column in a predicate. Let's talk about some of the extensions to list partitioning now. We now have a thing called automatic lists. So here, for example, I have a table called people, and I've currently got it partitioned in the familiar way by gender. So I have male and female. But as the world changes, I might want to offer in my application the ability for people to say, I don't want to specify my gender on your data entry form. So I can now have a thing called automatic, which simply, it's a bit like interval partitioning for lists. So rather than when I come along and insert a value which is not male or female getting an error, I'll actually dynamically create a partition. I should note we can't just create a table which is automatic with no partitions. You must have at least one, just like we have with range partitions and intervals. But now I come along, I insert a new record for unspecified, for example, and I'll dynamically create a partition called syspP661, which I could refer to using the for syntax if I needed to. We also have now what we call multi-column lists. Multi-column lists let you have multiple columns in the list definition. So now it's the pairing of these two values which determines which particular partition these go in. And just like normal list partitions, you can have multiple sets of values that go to a single partition. I should note that even though we have multiple columns, we still have a single default keyword. So if you're thinking that if I want to specify defaults, I would do something like this. It's on two columns, so I'd have either a value and default or default and default. We actually don't do that. Even if you have multiple columns, you only have a single partition that maps to this special value of default. The reason for that is, if I had this facility where this would be, I've nominated a camera, but something else as a catch-all for the second column, or in this case, I've got a value for the second column, but I've got a default for the first column. If someone inserted that, where would it go? It could sit in that one, or it could sit in this one. Therefore, we have an ambiguity. So as a result, we only have that single default and a single default partition. Now, here's where we got a little bit edgy. Maybe we have large amounts of data which motivate partitioning, but maybe we actually don't want to store it in Oracle. I know, you think I'm a monster suggesting something like that, but it's actually a reality of our times. We have a thing called polyglot persistence. What's that name? Polyglot persistence is really, a polyglot is someone who speaks multiple languages. Polyglot persistence is simply the ability to store things in different technologies. And Oracle itself embraces this. You might want to store some data in Hadoop, you might want to store some data in a NoSQL database, and obviously something in a relational database as well. As a DBA, you're going, oh great, thanks. So I have to learn Hadoop, I have to learn Spark, I have to learn Hive, I have to learn all these other technologies. Why can't I just use SQL and actually access it like the normal SQL facilities? And yes, you can. We have a thing called partitioned external tables. So now I can create a table so I can query it with normal Oracle SQL, yet all the data you can see here is actually external. The whole table is external. I use the Oracle loader driver to actually pick it up, and I can even nominate a default directory where it comes from. And then each partition nominates a file or multiple files. So this 2015 gets its data from a CSV file. I can even override the directory for certain partitions. So this particular one gets its data from an old data directory, not the default data directory. It's not just flat files. The data literally can be anywhere. I can actually now assign credentials, operating system credentials, to a particular table, which is then defined in a wallet. And that lets me now access, for example, partition of data across the network, for example, in a cloud-based object store. You have that increased flexibility now for where your data is, and yet you can still query it with the beauty of SQL. Now, I should note that if you're doing this, your responsibilities as a data custodian are increased, because if I do select star from orders for 2015, this particular partition, which is accessing external data, does anyone see the problem here? Yeah, in my external table, I've actually got some data that doesn't actually match the partition definition. And we can't validate that. We can't actually restrict that because it's just reading an external table. If I actually applied a filter here, the filter would still be applied. That data would disappear because this would be good enough to use partition elimination. So I'm restricting myself to that partition that we just saw, this one, which had the data. This one would actually still apply the filter, so the data would disappear. But I should note that data would not appear in partition 2017 because it's not in the files for 2017. So you start getting these data inconsistencies because we can't control what's in an external table. We do offer a data validation facility though, so you can run Aura partition validation for the row ID, and it will return you a 1 or 0 telling you whether this external data actually does subscribe to the partition definitions you've defined. So in this case, the 0 says, yep, the data in here does not map to the definition that you've created for this partition. At which point you're going, gee, thanks a lot. Now I've got two sets of data to look after. I've got all my relational data defined in my sales table. I've got all my external data sources defined in an external partitioned table. I've now got to query two data sources to bring a consolidated view together. Well, you actually don't. In 19C, we give you a hybrid partitioned table. That's a facility where you can have some parts of a table being external and some parts of a table being relational. The syntax looks a bit like this. It is actually an external table. So a hybrid partition table is by definition an external table for which you have some relational parts. So it's external. The first partition here, for example, comes from an external file. But these two partitions here in the green, they're just normal partitions. As a result, I can insert data into those normal partitions. They're just like relational tables. If I try to insert into the external components, then obviously I can't because they're external tables. They're not real relational tables. But now I can literally mix and match relational data with external data and reference it all from a common single table. That covers off some of the extensions and enhancements that we've done to partition tables since the basic core baseline has been established. Let's now dig into partitioned indexes and dig deeper there. As we said, we have global indexes or we have local indexes. We also have global partitioned indexes, which is the ability to actually create a partitioned index that doesn't necessarily adhere to the partitioning system of the underlying table. The underlying table doesn't have to even be partitioned at all. It's pretty rare except for one special case, and that special case is handling what we call extreme volume transactions. It's a hash partition index. When you have high volume transactions, automatic segment space management takes care of the distribution of data across the table. Because we scatter the blocks in the table, we can achieve incredibly high concurrency. But for indexes, it's a bit of a problem because you can't scatter index blocks because all the indexes have to be stored in order. So if you've got extreme ascending key sequences, which is really common, they're all competing for those one blocks and you have contention, which limits scalability. That burns a hole in your server, but hash partition indexes can fix this. You globally partition for example, a primary key sequence by hash. Now you effectively have 8 primary key indexes separated by hashes. You've distributed that load across multiple indexes. It won't impact performance because primary key lookups always go to a single value anyway. In extreme cases, you could even partition a table by the instance that's running it. So for rack, for example, if you partition your table by instance and set that as a column default, then you can have your primary key indexes also partitioned by instance. Therefore, you don't have any cross-instance chatter. I've seen demonstrations there where you're literally doing hundreds upon hundreds of thousands of inserts per second with literally no contention across rack nodes. We also have partial indexing now. You can actually create a table now and nominate this keyword, indexing off. The default is obviously indexing on. And then on a partition by partition basis, you can say, I want no indexing on this partition, but I do want indexing on this partition. This obviously would be the default in this case. I didn't need to specify this, but as you can imagine, you can nominate it on a partition by partition basis. Now, when I create my indexing, I simply say indexing partial, and it will respect those values that you nominated at the table level. Or I could even just do an alter index and choose it explicitly. So now some partitions are indexed and some are not. Why would I do that? Well, let me go back to my picture. This data might be so old that I only ever access it for trend analysis, so the whole year. So it might be a waste of time to index this data. I might do the opposite. I might index the old data, but not index the new data. Now that seems a bit strange, but one of the reasons you might do that is you might choose the new data and put it into the in-memory column store. Memory is obviously limited, so you might choose, I'll just put the recent data into in-memory and the rest has to be indexed because I haven't got enough memory to put in memory. And in particular, given that you can get in-memory for free in 19C up to 16 gigabytes, this becomes a really attractive proposition. Put your current data into the in-memory column store with no additional license cost and index your old data. You can even have a globally partitioned index that is partial. That seems almost weird. I've got a single index that spans the entire data, but I can have it partially indexed, which means some of it just doesn't exist, even though it's a single index structure. Why would that you do that? Because the optimizer is even aware of that. So if I do a query on a global index for customer equals 1, 2, 3, 4, normally you would expect to see something like this. Table index X by row ID for an index range scan. But if this chunk here doesn't actually exist, that obviously wouldn't pick up all the data. But the optimizer knows this. The optimizer will see a partially indexed global index and rewrite your query to do this. It'll say, for the part of the index that it does exist, I can use an index access. For the partition that for the index where it doesn't exist, I'll actually use a full table scan. So the optimizer is smart enough to know what part of a table is indexed and what part isn't, even if it's just a single index structure. A lot of cool things coming in index maintenance as well, but we'll see them later. Let's now dig into some of the cool things with partition queries. As I said, with partitioning pruning, we saw this. This is, everyone knows this. You pass in a literal, we can prune to get just the right partition as long as this is part of the partitioning key. Obviously, if you start putting expressions around your partition key predicates, then you get the whole thing scanning the whole table. Please, obviously, hopefully no one's doing this. Nominate that partition key in its unadulterated form. But it works with a whole stack of things as well. It works with binds. If you have a nominated partition key of a bind, you'll see this key in there, but it is a partition range single. We can still jump into just the right particular partition. There's a lot of power here. It works with things that are even as complicated as this. I've got some ranges here and some OR. You'll see this kind of information in your explain plan. We're doing a partition range OR. We're still accessing just the relevant partitions as opposed to the whole table. If I do an in list, you'll see this in the plan. Partition range in list, key in. Once again, just hopping through the particular query, partitions that are required. There's an interesting thing with interval partitions that might scare you, but there's nothing to worry about. When we have range partitions, as we saw, we know that the range is defined by the previous partition and the definition of the current one. With intervals, it's different. Every partition is defined with a fixed length. So even if these two partitions don't yet exist, they theoretically exist in the database from the database's perspective. So as we know, every table can have at most 1 million partitions. So you can think of an interval partition table as having all those partitions already defined, they just don't physically exist yet. So if I create a table called sales with a single partition and its interval partition, there's no data in it yet. I've just created it. You'll see this in the execution plan. I'm going to scan partition 1 up to partition 1 million. Yes, there are 1 million potential partitions in there. Well, obviously they don't exist yet, so don't panic when you see these kind of numbers for interval partitions. We also have smart IO avoidance. If I do select star from, and this is a non-existent partition, you'll see we don't even touch the table at all. We do partition range empty. We actually don't even touch the table. We get instantaneous response. We can even prune by subquery. If I have the sales table which is partitioned and I join it to a non-partition table or even another partition table, we see this kind of stuff in the execution plan, which says, yes. Now, what on earth does that mean? What does BF mean? BF stands for Bloom filters. Bloom filters are a space-efficient probabilistic data structure that is used to test whether an element is a member of a set. I have no idea what that means. Let's walk through it with an example. Here's a metaphor of how Bloom filters work. It's really the same as phoning up in advance to go to the movies. Let's say you want to go see the latest Wonder Woman movie, which is coming out later this year. You phone ahead, won't you? That's what you do. You know, when a movie's that popular, you're not going to just roll up because you phone ahead and you say, are there any seats? And they go, no, it's a premiere movie. The thing is sold out. You can't get in there. I've saved myself some effort by phoning ahead. I didn't actually drive down to the cinema and try to get in. Now, of course, when I phone ahead, they might say, look, if you're quick, get down here. There's a few seats left. But when you get down there, it was sold out anyway. That's what a Bloom filter does. It tries to avoid you having to do work by, like, for example, phoning ahead. So it guarantees you that there's no way known you would be allowed to drive down to the cinema if it's definitely sold out. It saves you that effort. So most of the time, it should save you that effort. However, it's no guarantee. There might be the occasional time when you actually, it says, yep, I reckon you're good enough to get in there, and you drive down there and actually you can't. So let's look at that from an Oracle perspective. If I'm joining sales partition table to the employee table, as I'm scanning the employee table looking at some dates that are the join key, I'll put them through what we call a Bloom filter. It's a function which goes into our Bloom filter mapping, and it basically creates a number of entries in this Bloom filter. So as we scan through, all these dates map to these particular points in the Bloom filter. I then scan through the dictionary definition for the sales table, taking each of its partitions and put them through the Bloom filter. So this is not the whole sales table, just the different definitions of each partition. They get put to the Bloom filter as well. And then what we do is we simply look for matches. Those three matches tell me that only these three particular partitions will be relevant for the rest of the query. So now they might map to partitions 2, 6, and 7, and therefore I only need to scan these particular partitions. Bloom filtering is a way of eliminating partitions from consideration. It's that way of eliminating false positives. These partitions here, which didn't match up, you can think of them as, yep, they are sold out. You'll never by definition need to touch them. There are other query benefits as well. We have a thing called a partition-wise join. Partition-wise join lets me join the partitions instead of joining the table. Big deal, you say. Let's look at another metaphor to explain the benefits of that. These are my glorious children from some years ago, and being little boys, they leave a mess in their room. So what if I need to join the socks? I need to find the pairs. If I'm trying to match the pairs as I'm cleaning their room, I pick a particular sock, and now what do I have to do? I have to go through every other single sock to try and find all the pairs. It'd be better for me if I could partition the socks into black, white, and everything else, for example. So now when I have to find the pair for that sock, I only have to look in the black socks. That's obviously more efficient. I don't have to scan the other socks. That's called a partition-wise join. I only have to join inside a particular partition. This is what we call a normal join. I'm hash joining here, but before I do the hash join, I scan all the left socks and all the right socks. That's a non-partition-wise join. If the two tables match exactly on partitioning, I can actually do what we call a partition-wise join. For each partition, I do a hash join of each partition, so it's far more efficient. Let's finish off now with partition maintenance. We'll dig in a little bit more into that. We have read-only partitions now in the Oracle database. What we used to do, and you can still do this, is you might take a particular partition and move it to long-term storage and then make that, for example, table space read-only. You might do that because then you don't have to back it up anymore with, for example, Armor, and you might shrink your backup windows. Nowadays, you can take a table and take a particular partition and make it read-only. Now you might be thinking, what's the difference? Well, there's no, it sounds the same as putting it into a read-only table space, but here's the difference. Even though it's read-only, which means you can't do DML on it, you can still do operations on it. I can compress it, I can move it, I can do other things like control the indexing on it. It's more flexible than just banging it into a read-only table space, which means it's untouchable. We have seen things on Exchange partition now. When we come to handling new data, we know about Exchange partition. What we do is we create a table in isolation, and then we do flip it to put it into the existing table. That's Exchange partition. But sometimes you can, and guess what? Sometimes you can't. You're going, huh? Why would you not be able to do Exchange partition? Let's look at an example. I've got a partition table here called par. It's got two partitions P1. I'm going to create a table that's going to exchange into it as a replica of par. It's got the same two columns. I try to exchange partition and it says, no, you can't. That's a bit strange. Maybe there's some validation that needs to be done. So I'll take off the validation. Still won't let me do it. Let's go look at user tab columns. Column 1 is X, column 2 is Y. On my exchange table, 1 and that, they look the same. The problem is I'm looking at user tab columns. If I looked at user tab cols, I would see this. The partition table has this strange hidden column, which came from this. It used to have a column called Z, and some time ago, I decided to set it to unused because I didn't need it anymore. Because, as we know, we never ever drop columns, and if you don't know why you should never drop columns, go to that link, bit.ly drop column. It's a video explaining why you should never run the drop column command. That's no problem, you think. What I'll do is I'll add a column called Z to my exchange table and I'll make it unused and then I'll try exchange it. Doesn't work. You have to be very, very precise to get this to work. I need to create that column in the second position, just like it was in the partition table. Now I can set it to unused, and finally, I can do an exchange partition. That's a lot of digging around, and it could be a lot worse because a lot of columns can be hidden for other reasons. If they're invisible, if you've done fast add column default, if you've done stats extension, there's lots of hidden columns that might occur in your tables without your knowledge. The cool thing is you can now say, I'm creating a table that I want to exchange. I simply say, create this table for exchange with table par. We'll go look at this table and find all the hidden characteristics and copy them into this exchange table. And now I can exchange it straight away. We've made some enhancements to drop partition as well. If you're dealing with ILM, Information Lifecycle Management, when you come to drop a table, you drop a partition, normally it breaks the entire partition, which is a bit of a drama because you now know the entire index. You can choose to keep the index valid by doing update indexes, and that will work. The index will stay valid. What it does is very carefully goes through and prunes all this stuff out, but guess what? It's going to take an hour and 17 minutes to do it because really it's just a giant delete going on. We're doing the cleanup for you. We now have a thing called asynchronous cleanup, which means you can run that drop command and it's instantaneous. Now, what about all this cleanup that needs to get done? What happens now is we just leave the dirty rows there. You'll see it in this index. It now has orphaned entries. It says yes. Someone's going to clean that stuff up, but luckily it doesn't have to be you. What happens is there's a DBA scheduler job that comes along now each night and does cleanup of all the global indexes. So we simply defer their operation to outside hours. Your index is left usable and you can still use all the other components of it. Truncate has been improved as well. In the old days, if you wanted to truncate a reference partition table, you'd have to start at the bottom and work your way up. That's 7 truncate commands. Nowadays, you simply do truncate cascade, the parent, and it will truncate all the way down, no problems. Similarly, exchange has been enhanced through exchange partition cascading in reference partitions. If I want to exchange this set of partition tables into here, I can literally do a cascade option as well. So we can now do all these cascading operations with reference partitions as well. Split and merge have been enhanced as well. There are no more limits now on the number of things you can merge or split. It used to be you had to pick just 2 to either merge or you could split into just 2. Now I can tick, for example, all the partitions for a month, the daily partitions, and merge them into a single monthly partition as well. Big deal, you say. Why would that be of interest? Well, all partition operations now can be done online. So I might have a table of sales where I want to have a very granular partitioning mechanism. For example, just by the hour. 24 hours later, I've got 24 partitions. A year later, I've got a whole lot of partitions. But now I could create a little, for example, bit of PL SQL there, which will generate me the DDL to actually merge hourly partitions into dailies and then dailies into month, etc., and do all this merging online. By having very granular partitions, I could, for example, do away with the need for a lot of indexing strategies because queries would now query just by the hour or just by the day or just by the month. Not only are they all online, they're also less impactful because now, for example, when I drop, for example, an index on a partition table, I can defer the invalidation. So any queries that were not using this index on my partition tables will not be marked as invalid. And there's a lot more of these coming. The idea being that as you do operations on one partition, cursors that were only referencing other partitions won't need to be reparsed. Speaking of online, we're just about done. Hopefully this has got you all super excited about, some of the cool things with partition tables, but what if your tables currently aren't partitioned? I'm going to have a big outage to do it or reorg all my tables. You don't. You can partition an existing table now with one command. Here's a table called T. It's not partitioned. It's got a couple of indexes on it, which obviously are not partitioned either. I can simply say, alter table T modify. I want to now partition by a new range and have an interval partitioned as well. And I'd like that oldest partition compressed. And I'd like to create take those existing indexes and make them, for example, partitioned. One of them's going to be local, one of them's going to have a totally different partitioning strategy. Oh, and by the way, while I'm doing it, I'm only going to copy over the newest rows because I'd like to archive the others off. I don't really care about them anymore. And I want to do the whole thing online with no interruption to service, and the database just goes, yeah, no worries. It's insanely good what you can do with online operations now in the Oracle database. Let's wrap it up because I've just about run out of time. There's huge amounts of potential here, as you can see. Huge amounts of benefits, hopefully, and hopefully this gets you excited about some of the cool things you can do with partitioning. Did you notice this presentation in itself was partitioned? We did the baseline, we did the tables, we did the indexes, the queries, and then we finished off with maintenance and online operations. I'm done. That was a whirlwind tour through all the fantastic goodies that have come through partitioning. Thank you very much for your time. We obviously don't have much time for Q&A because the next speaker needs to come on. So please hit me up on Twitter if you need to have any questions or reach out to me. And yeah, if you want a dedicated session on any particular topics, reach out to me and we can do it for your customer site. Thanks everyone for your time, and I'll hand back to you, moderator.
Thank you everyone for your participation today, and please do not forget to register for another great session in the conference and to interact with the speakers in their playback session page. Please enjoy the rest of the conference.